The only formula you only need to know is this one right here.
Can you move it down? I can't see all the things.
Oh, sorry. Right here. These are the formula you need to remember. Matrix A multiplied by an eigenvector is equal to a scalar, which is the eigenvalue and that vector itself. And the eigenspace are the space containing of the eigenvectors, and they have to have a specific property, is that they have to go through the zero vectors. By going through the zero vectors mean that the determinant of the eigenspace is always equal to 0. So that's one thing to know. So the question probably you would see on the exam is just if this eigenvector if this eigenvalue is in the matrix. So back to the image reference, the image we can represent in terms of the matrix A, right? And the scalar of the features we want to find, I gave it as 2. I just want to find, okay, given this scalar, I want to check if the scalar is in that image or not. A way to do it is just using this formula, ax equal to lambda x. If we have ax equal to lambda x, we can find our ax minus lambda x equal to 0 or not. If these two are equal to 0, the determinant of them equal to 0, that means that the eigenvalue is in the matrix we want to check. So if I ask you an eigenvalue, I give you a 2 by 2 matrix. A short way of doing it is you just minus the eigenvalue diagonally. So I have a 3 here, I have an 8 here, I minus 2, I have 1 and 6. The rest is remain. And I want to check the determinant of this if that are equal to 0 or not. And by just looking at it, I can tell 1, 3, and 2, 6 are the same. They are scaled back to 1, 1, 2, and 1, 2. So the determinant of this entire matrix, don't worry about 0. I'm just solving for 0 here, is 0. By knowing that, I can say, yes, this eigenvalue 2 is in the matrix A. Same for here. If I ask if the eigenvalue of negative 2 is in this matrix, I just minus the negative 2 diagonally in this direction. So 7 minus negative 2 is 9. Negative 1 minus negative 2 is 1. So I got 9, 9, 3, 3, 1, which are scaled into 3, 1, 3, 1. And the determinant of that is 0. Okay. That's the eigenvalue. What if we want to check the eigenvectors? We go back to the same formula. Ax equal to lambda x. We want to find our x right here. And we do the same. So we have a minus the lambda of I multiplied by x is equal to 0. If we just performing this, we're also solving for x by just using row reduction. So if I want to check if this vector's eigenvector of 1, 4 is in here, let me see. Well, okay, this question didn't give eigenvalue, my bad. We want to check if this 1, 4 is an eigenvector of this matrix A. I'll have to do the multiplications. So we'll need this. We just multiply A equal to x to check if our x has a scalar value back to it. So what I mean is that this is my A. These are vectors that I want to check. I just do matrix multiplication of A and x, which gave me 1 and 35. If you guys look at the original vectors of 1 and 4, 1 and 35 doesn't have a relation to 1 and 4 because you don't have a scalar that add up to it. So it's like from the images, there's a random column outside of the image. We don't care about, we throw it away. So that is not a feature in the image. So this is not an eigenvector of the matrix. Is that clear? We just do, for eigenvalue, we do the minus, we find the determinant. For eigenvectors, we given an eigenvector, we want to do matrix multiplication and compare if we can make a correlation with the original through a scalar. Okay. I would not give this type of problem because this is what I was given during my last semester. And I have to like use my head a lot to figure out how do I scale this back to get this square root of something. So don't worry about seeing this. But for this type of question, the answer is yes. After this, what my multiplication result is, and then from there I have to think how can I relate to this original one. But you guys don't have to worry about it. So now we know that how to check an eigenvalue, how to check for an eigenvector. We want to find the basis of the eigenspace. Eigenspace, yes. So the symbol for it is P. P stands for all of the linear independent eigenvectors in that, and it's comprised of the basis of them. We call them the eigenspace. So how to find the eigenspace? If the question already given us matrix A and two of these eigenvalues, what we want to do is we want to find the basis for each eigenvalue. So right now I'll try with, this is the previous formula that I mentioned. I want to do the minus, and I can find my x using row reduction, right? So that's what I was trying to do for the last one. So given my A, given an eigenvalue right here is 3, first I have to check if that 3 is the eigenvalue of this matrix or not. But probably in the exam is already in there, so you guys don't have to worry about checking it or not. I just do a minus 3 again. So minus 3 in the diagonal direction, 9, 6, 3, 0. I got this. And we already know that just looking at this, the determinant of that is already 0. So we know it's an eigenvalue of it. How do we find our basis? The professor mentioned that we can just find using our free variables right here. If I shrink my matrix back to 6 and 0, 0 and 0, I would say my x1 is equal to 0. My x2 here is a free variable, so I can use my x2 as the basis for this eigenvector using from the eigenvalue of 3. So if you guys doing the minus A, your matrix A right here, you minus the eigenvalues, and you turn it into the basis using free variable, you can find this equation right here and say that x2 is free, and we can use x2 as our first vectors in eigenvector. So my x1 and x2 can be equal to, erase that, x2 of 0 and 1. You guys remember how to turn free variable into this, right? Yeah. So once you guys know that, okay, first of all, my P, I can find my V1. So V1 is done using an eigenvalue of 3. Now I want to use the eigenvalue of 9. So I have to find the basis for 9 right here. I do the same. I just minus 9 from the original A. So there will be 0, there will be negative 6. 0, 0, 2, negative 6. The determinant of this is 0, so we go on to the next step. We can say that my x1 is 3 times x2, so I can also use x2 as my next variable. We don't have to decide which one is our variable. We just need to compromise all of these such that they are linear independent. So right now my x2 is, from using this, I can say that my x2 is the basis for the eigenvectors of 3 and 1. So now I have my v2 is 3 and 1. So that's my v1 and v2 for the eigenspace. And they have to be linear independent. Any question on that? Very good.
Is there anything we have to do to make it linear independent if it isn't?
It should be linear dependent, because if it's not, that means these probably are not the eigenvalue in the first place. And also, if you guys notice that my v1 is a 2 by 1, right? My v2 is also 2 by 1. And if I have them in my eigenspace, it will be a 2 by 2. And what is my original A? A 2 by 2. So if my eigenspace is the same size of my original matrix, then it's correct. If it's not, this matrix is not diagonalizable. Okay. So just make sure the shape of your eigenspace is at least equal to A. And that is for a 2 by 2. I would just stick with 2 by 2 because they are the easiest one. A 3 by 3 would require you guys to minus the diagonal the same here and then try to find the free variables for each one, which might be long, and I don't want your last quiz to be that long, so I just stick with 2 by 2. But if you guys want to take a look at them, it's in the book, and I would recommend to. Okay. Next is characteristic of the eigenvalues. So given this vector A right here, we want to know what is the eigenvalue of it. Previous question I already either give you guys the eigenvector or the eigenvalue. But what if we want to find it from the original matrix A? We just bam this formula into it all the time. Just having this in your mind, use it preview. So now my original A is right here. If I want to find my eigenvalues, I just minus the lambda. And now what we remember that for an eigenvalue to be in that, when we do the minus, the determinant of that has to be 0. So I want to have, let's call this B, matrix B. My matrix B has to have a determinant equal to 0. So a determinant of the 2 by 2 is straightforward. We multiply this and then we minus the opposite diagonal. So make sure to know how to do basics math, because that will be on the quiz. From here, if I do 2 minus lambda multiplied by 2 minus lambda and then minus 49, yeah, I would get this. Why did I wrote 45 here? Oh yeah, that's right. Yeah, that's right. Negative 45. So this is what probably you guys would see on the quiz, not the exact equation, but is the approach in your solution. And from here, you guys want to solve for lambda. Just solving for lambda. So the approach is you first minus your matrix with lambda, and then you solve for the determinant of that equal to 0, and then you solve for lambda. Solving for lambda. So for this question, I would get my lambda equal to negative 5 and 9. And a tip for solving this is, it's a good formula I always remember. So here's a sample question like this as well. And when I want to find the lambda, I would first get into this form, right? And from this form I can say, okay, here my A is equal to 1, my B is equal to negative 16, my C is equal to 48. I want to find two values that I can group them in together to find my lambda easier. So I would just try to solve this equation. My x multiplied by e is equal to a and c. So a and c, which is 48. X plus e is b. So right now b equal to 16. If I know this equation in heart, I can solve for x and y. And knowing this x and y, what does this do? I can group them. So from this equation here, I can group them into my x and y and solve for lambda. But if you guys already can do this easily, then you guys don't need to know this. But this is what I usually do. So that's just 5.2, how to find an eigenvalue from a matrix. And if you guys can already find the eigenvalue, finding the eigenvector is the step above here, where you do the minus and then you try to find the free variables. So that's the eigenvector. So this diagonalization is the last part of today. we want to find A using this formula right here. So in the quiz, P right here is our eigenspace. Our D right here is the diagonal matrix of A. Question on the quiz would probably, given P and D, I want you guys to find A of 5 or A of 4, something like that. Or I can just ask you guys to find D and P only and don't have to compute A of power of something. So back to the previous portion, A can only be diagonalized if our P has the same size as A. So remember, if I make my eigenspace is a 2 by 2, my A is also a 2 by 2, then this formula is valid. If on the quiz, if I make it tricky and then when you guys compute P, you would get like 2 by 1, and then my A is 2 by 2, and I ask you guys to find A of 5, don't find A of 5. Just say this question is invalid. So now, given A, how can I find my D? How can I find my P? D right here is just your regular diagonal matrix using eigenvalues. So remember, from the previous one we have right here, we can find the eigenvalue, right? Once we have all of these eigenvalue, that's just our D. We just write our diagonal matrix in terms of all of the eigenvalue diagonally. And our P right here is just the eigenvector we can generate using this eigenvalue, the basis vector we've seen previously. So yeah, given if we can find our eigenvalue, we can generate all of the basis for the eigenspace. So we already find B and D, so we know them. And this is the only tedious part of finding A of K. Using this formula, we can also find our A of K, and in the book they prove that A of K is only adding K into this formula right here. So that's the point of diagonalization, is that whenever we want to generate our original matrix, scale it up to power 2, power 5, power 6, instead of doing 6 times of that multiplication, we only need to do 3 times multiplication, and we only need to add this up. So let me see some example I can find. Okay. So right now, I want to find my A power 4. I already given you guys P, D, and now you guys need to find P inverse. So we're trying to find A of 4 using this formula that provided previously. And what you guys need to know to make sure is to do matrix multiplication correctly. So the order is that always start from the right, going back. This is my P, this is my D, this is my P minus 1, the P inverse. I want to compute my D and P inverse first, and then I will multiply by P. It always goes right to left. So just careful with that. Once you guys can compute that, and also this is my D, right? D of 4 is just 2 power 4, 1 power 4, 0, 0. So that's straightforward. You guys have this. You guys do multiplication right here, and just all of the multiplication you guys can do, and that would just get us. So now here is my D, P4, B minus 1, P inverse, my P. If I do all of them, I would get these ugly numbers right here for the matrix, and this would be my A of 4. So on this section or in the quiz is just knowing multiplication basically. So probably this will be in the